part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to describe how to construct the Green's function for a two-dimensional Laplace's equation. In particular, I'm going to write down the Green's function for the system of a very long rectangular pipe of dimensions a by b. So the equation that we are going to solve today is the second partial derivative of the Green's function with respect to x plus the second partial derivative of the Green's function with respect to y is equal to minus delta function x minus x prime times the delta function y minus y prime. And by the way, it's Green's function or Green function. You probably heard it both ways. Anyway, the Green's function is a function of both the unprimed and primed coordinates. Unprimed coordinates, of course, have to do with the observation point or field point. Prime coordinates have to do with the source. In order to synthesize the Green's function for a two-dimensional system like this, we're going to make use of the one-dimensional solutions. Now, in previous lectures, we covered some techniques for writing down the Green's function in one dimension. And so I'm going to sketch out the more general expression and then write down the expressions that are specifically useful for this problem. Okay, so just a reminder, in one dimension, the Green's function satisfies this inhomogeneous Sturm-Liouville equation. And here are the functions p, q, and sigma are just functions. We're not ascribing any particular physical meaning to them. This is the derivative with respect to x of the function px times the derivative of the Green's function with respect to x plus the function q of x plus lambda times the function sigma x times the Green's function, and that's equal to minus the delta function of x minus x prime. So basically, the Green's function is the response of a linear system to a unit source, okay? And the homogeneous expression, and here I'm just going to drop the dependence on x and x prime, or rather just x, because I want to save myself a little bit of space in the board. So this is the homogeneous Sturm-Liouville equation, and again, this is more general than our Laplace's equation or Green's function for Laplace's equation. Remember, many mathematical physics equations can be put into the Sturm-Liouville form. So for the problems that we're interested in, p is going to be equal to 1, q is equal to 0, and c is going to be equal to 1. But I'm going to leave it in this more general form for right now. Okay, so the goal is to write down the Green's function, and I'm going to solve this equation. So we made the case that Green's function could be expanded in the eigenfunctions to this equation. So we're assuming that we've got certain boundary conditions, and since we are talking about one dimension, let's say that our boundaries are at x equals 0 and x equals a, and our conditions are that the eigenfunctions vanish at x equals to 0 and x equals a. Okay. And then we came up, derived an expression for the coefficients a of n. ultimately, green function could be expanded in the eigenfunctions, and that had the form minus summation n equals 1 to infinity of psi n of x prime, psi n of x, all over lambda minus lambda n. Okay, a couple of things you want to notice about this is that the Green's function is symmetric in x and x prime, and furthermore, it has poles at the eigenvalues lambda of n. So that was one expression that we used, or we derived and applied to a specific problem. Now, another way to write the Green's function is to say, well, okay, I've got two solutions, okay, and one of the solutions satisfy the boundary condition at x equals 0, and the second solution, and there are some constants out in front, satisfies the boundary condition at x equals a. And ultimately, we derived a second form of the Green's function, and that was equal to minus psi 1, which satisfies the boundary condition at x equals 0. And that is a function of x less than. X less than refers to the smaller of x and x prime, and psi 2, which is a function of x greater than, that refers to the greater, which is greater x or x prime. And this is all over p of x prime, and that's just this function p here in the Sturm-Liouville equation, and w is the Wronskian. And we'll write these functions as functions of x prime. So we've got psi 1 times the first derivative of psi 2 minus the first derivative of psi 1 times psi 2. Okay? Okay, so this is method 1 over here, eigenfunction expansion, and over here this is method 2, which is writing Green's function down using the Wronskian. Okay, so those are the general expressions, but we want to apply this to a rectangular pipe. So what I want to first do is recall what the solutions were for the one-dimensional problem of the second derivative of psi with respect to x plus some constant out in front of lambda times psi. That's equal to 0. And the Green's function counterpart of that equation is equal to the second derivative of the Green's function plus lambda times g equals minus delta function of x minus x prime. Okay, so specifically we're looking at this problem, this region of space. So let's either erase some of this. I'm going to go ahead and write this up on the right-hand side of the board. And for brevity, I'll just leave off the arguments here. But anyway, those are the two representations of the Green's function in one dimension. Okay, so let's take a look at that first expansion. And we need to solve this homogeneous equation for the eigenfunctions and corresponding eigenvalues. So if I look at that, what is the solution here? Well, psi of x is equal to some constant. Immediately I see that's just going to be a linear combination of cosine and sine. So say this is a sine square root of lambda times x plus b cosine square root of lambda times x. Okay, first boundary condition is that sine must vanish at x equals 0. Well, this first term automatically vanishes, sine of 0 is 0. Cosine of 0, however, is 1. The only way this condition can be satisfied is if we set b is equal to 0. So this term will drop out. Second condition is that sine is equal to 0 at x equals a. The only way that can happen is if lambda, square root of lambda, is equal to n pi over a. Or, it's the same thing, lambda n, write it with the subscript n, is equal to n pi over a quantity squared. So we've almost determined what psi is. These are going to be, these functions are going to be orthogonal, but we also want them to be normalized as well. And integrate from 0 to a, and this is psi n of x times psi n of x d of x is equal to 1. I substitute these in there. I do the math myself for a. A is just going to be equal to square root of 2 over a. So I'll leave this up here just for a minute before I erase it. Therefore, my eigenfunctions are going to be square root of 2 over a, sine n pi x over a, and then the corresponding eigenvalues are going to be lambda n, and those are equal to n pi over a squared. Using the first expression for the Green's function, and I think I'll write it over on the right-hand side of the board. Minus the summation n equals 1 to infinity, 2 over a sine n pi x prime over a, sine n pi x over a, all over lambda minus n pi over a squared. Now the second representation of Green's functions, well, you need to find a function that vanishes at x equals 0. And as it turns out, that's just going to be equal to sine square root of lambda x. Now the second function has to vanish at x equals a. So another choice, or a different choice, would be sine square root of lambda a minus x. And this should be x less than, and this is x greater than. And a minus sign out in front. It's also over p of x, but that's just equal to 1 for the equations that we are investigating. And I need to calculate the Wronskian. Let me write this down here. The Wronskian in this case is equal to sine square root of lambda. And we'll do this in x prime. But we take the derivative of second function with respect to x prime. So this is going to be cosine square root of lambda a minus x prime. And then we also have a minus out front due to taking the derivative. And then the second term is also going to have a square root of lambda out in front, just like the first one. And this is cosine square root of lambda x prime sine square root of lambda a minus x prime. So when I use a trigonometric relation, I can combine both terms into a more compact form, and that's going to be equal to square root of lambda, or minus square root of lambda sine square root of lambda a. And these minus signs will cancel out. And those are the two representations in one dimension. I'm going to leave those on the right-hand side of the board because I will use those to write down or construct the solution in two dimensions. Okay? Begin in a likewise fashion. We'll tackle the homogeneous equation first. So this is just Laplace's equation in two dimensions, and the usual way to solve that is by separation of variables, which means we assume that the function psi can be written as two functions, or the product of two functions. One function that's only a function of the variable x, and one function that's only a function of the variable y. When I make this substitution into Laplace's equation and divide through by psi, I'll have 1 over the function x times the second derivative of the function x with respect to the variable x plus 1 over the function y times the second derivative of the function y with respect to the variable y. And that has to be equal to 0. The only way this can happen is if this term is equal to a constant and this term is equal to a constant. So I will call this first term minus lambda x and the second term minus lambda y. Hence, I will have 1 over the function x times the second derivative of the function x with respect to the variable x is equal to minus the separation constant lambda x. So I can multiply both sides through by the function x, and then also move this term over to the left-hand side. I'll just wind up with second derivative of the function x with respect to the variable x plus lambda x times the function x is equal to 0. And I have differential equation for the function y that has identical form. And the constraint on these separation constants is that their sum is equal to 0. So lambda x plus lambda y is equal to 0. Now, what the solution to these equations, or the solutions are, basically be written as some linear combination of cosine and sine, which would fit our particular boundary conditions. And I can write down the counterparts for the Green's function. Again, notice identical form to when we were just treating the one-dimensional case. So It's the second derivative of the Green's function that's only a function of x and x prime with respect to x plus lambda x gx equal to minus delta function x minus x prime, and an equation for the Green's function that's only a function of the y and y prime down here. So let me just leave this up here for a minute. Basically, what you'll see is when we write these, the Green's function down, or eventually derive it, is that there are different representations of the Green's function, and there are actually different approaches to solving this problem. I'm going to begin by making an expansion in terms of eigenfunctions. So in other words, because we've already determined that the eigenfunction for the one-dimensional solution, and this is for a problem where you had x went from 0 to a, that's equal to square root of 2 over a sine n pi x over a, and then the eigenvalue, corresponding eigenvalue, is equal to n pi over a quantity squared. So the Green's function that I write down is equal to summation n equals 1 to infinity. We've got some coefficient times those eigenfunctions in x, but this coefficient it now just doesn't have x and prime appearing in it. It's going to be a function of y, okay? So that's the difference from before we wrote down the Green's function in eigenfunction expansions over here. This coefficient a of n obviously didn't have a y dependence here. Okay, so I'm going to have to erase this stuff on the left-hand side of the board. And I'm going to substitute this into this differential equation. And I'll pull the summation sign out front when I take the second derivative of g with respect to x. That's going to leave the coefficient a of n untouched. And it'll be times the second derivative of the eigenfunction psi of n with respect to x. When I take the second derivative of this expansion with respect to y, that leaves eigenfunction psi n untouched, so second derivative of the coefficient y with respect to y, and then over the right-hand side I have minus delta function x minus x prime, delta function of y minus y prime. Well, I already know what these eigenfunctions are. They're equal to square root of 2 over a sine n pi x over a. So when I take the second derivative of that with respect to x, that is going to give me an additional factor of minus n pi over a squared out front times sine n of x. I'm going to factor out the sine n of x, or pull it out of the brackets rather, and switch the order of these two terms. Okay, let's see, coefficients that I'm seeking here, I'm going to extract this equation here from the summation sign, and in order to do that I'm going to make use of the diagonality of the eigenfunctions, multiply through by a psi n of x on both sides. And we'll integrate from 0 to a. And basically I can pull this in the summation sign because this particular factor doesn't depend on x. So I can write it like this. When I do the math here, this just gives me Kronecker delta. See, this factor here will be equal to 1 when n is equal to n, 0 otherwise, so that it has the effect of picking out the term from this series when n is equal to n. Over on the right-hand side, when I integrate over this, the delta y minus y prime can be pulled out in front. When I integrate it over the product of the function sine m of x and delta x minus x prime, and that just basically picks out that one particular x when x is equal to x prime. So on the left-hand side, I'm going to have second derivative the coefficient a of m with respect to y minus n pi over a, which pertains to the dimension, times the coefficient a and y. Okay? If you compare this expression with the Green's function, notice the similarity in form. In fact, if I were to say that this function a m with y could, basically you can just pull this factor of sine m x prime out, and see, that's equal to some Green's function. That's a function of y and y prime. And I'm going to make this in subscript explicit because that dummy index is actually going to appear in the expression for the Green's function. Okay, so when I make that substitution then, we'll wind up with an equation that is identical in form. Okay, so the only difference is this is a function of y instead of x. Also notice we've got a minus sign here as opposed to a plus sign in front of lambda. Okay, so I'm going to go ahead and solve this using this expression over here, using the Wronskian. Okay? So in order to make use of this, and wanting to note that, well, this is written in terms of x and x prime, we're solving an equation in terms of y and y prime. Moreover, this lambda here was positive, and here we need to take account of the minus sign. Okay, so when we do that, this Green's function then okay, let me stand out of the way here. And notice the substitutions I make. Because it is a function of y and y prime instead of x and x prime, I've replaced the x's with y's. Moreover, where you see a up here, I replace those with b because this Green's function is over this interval going from 0 to b. And you might be saying, well, what about this factor of a? Well, that's because that's what we're substituting this factor out here from the second term in for square root of lambda. And indeed, that's where this I comes from because of the minus sign out front here. Now, if I make use of the fact that sine ix is equal to I sinh x, we'll have a factor of I from here, here. I've got an I here, and then a factor of I here. So all those cancel out. And the final result for this Green's function in the y direction is going to be sinh n pi over a y less than sinh n pi over a b minus y greater than all over n pi over a sinh n pi b over a. So all I need to do at this point is just combine everything together. I know what the coefficients a and y are, I know what my eigenfunctions are, and I need to erase this. Up here. And because each of these factors in here has, or each of the eigenfunctions rather, has a factor of square root of 2 over a, that's just going to be 2 over a. So this 1 over a out front is going to cancel with this 1 over a in the denominator. And furthermore, I'll pull this factor in pi just out here. Let me read this off. This is going to be summation n equals 1 to infinity. 2 over n pi sine n pi x prime over a sine n pi x over a sinh n pi over a y less than sinh n pi over a b minus y greater than all over sinh n pi b over a, okay? So that's one representation of the Green's function that satisfies the boundary conditions that the Green's function vanish on each of those surfaces. And there's nothing special about expanding in x. We could have expanded it in y instead. It's a good exercise to go ahead and work that out. Again, the derivation is going to be identical. I'm going to go ahead and write down the solution. So to write down the equation without actually going through the derivation, all I need to do is just to replace or swap the x's and y's and then swap the a's and b's. So therefore, the second representation, if we had expanded in terms of eigenfunctions that were a function of y instead of x, this would be summation n equals 1 to infinity, 2 over n pi out front again, sine n pi y prime over b, sine n pi y over b, sinh n pi x less than over b, sinh n pi over b, a minus x greater than, all over sinh n pi a over b. So two representations. I can write down a third representation, and that will be a double expansion. Let me leave everything up here just for a moment before we move on, okay? Write this as summation n equals 1 to infinity, summation n equals 1 to infinity, the coefficients c and m, sine n pi x over a, sine n pi y over b, and I can substitute these into my differential equation for the Green's function. When I take the second derivative of this expansion with respect to x, that's going to give me a factor of n pi over a squared minus sine out front. And likewise, when I take the second derivative with respect to y, that's going to give me minus n pi over b squared. And I'll have sine n pi x over a and sine n pi y over b, and that once again is equal to delta function x minus x prime, delta function y minus y prime. In order to extract the coefficient c and m, I'm going to make use of the orthogonality. I'm going to make use of the orthogonality of both of these sine functions. Therefore, I'm going to multiply through by sine, we'll say n prime pi x over a and sine n prime pi y over b, and then integrate from 0 to a and from 0 to b. I can pull the integral signs inside of the summation. And one other thing you want to notice too, this has a minus sign basically, and that has a minus sign, so let's get rid of those. Okay, so this is takes up a little bit too much room here, but anyway, let me just read this off. Summation n equals 1 to infinity, summation m equals 1 to infinity, c and n, brackets n pi over a squared, n pi over b squared, integral from 0 to a as sine n prime pi x over a sine n pi x over a dx. We have dx twice, we need that twice. Over here we've got integral from 0 to b, sine n prime pi yb, sine n pi y over b, and over the right-hand side, we've got the integral from 0 to a, delta function x minus x prime, sine n prime pi x over a dx, and integrating from 0 to b on the right side, delta function y minus y prime, sine n prime pi y over b. Okay, so after all this, when I do the math here, this is going to give me a factor of a over 2, and this is going to give me a factor of b over 2. It's going to give me sine n prime pi x prime over a, and this is going to be sine n prime pi y prime over b. And I've got delta functions, Kronecker delta and Kronecker delta function m prime. Okay, so that will have the effect of extracting those terms for which n is equal to n prime and n is equal to n prime. And I'm going to go ahead and drop off the primes because after all, these are just dummy indices. So when I do the math here, okay, there's your solution. Okay, so use your green function in 2 dimensions, written as a double summation, n equals 1 to infinity, n is equal to 1 to infinity. 4 over ab sine n pi x prime over a, sine n pi x over a, sine n pi y prime over b, sine n pi y over b, all over n pi over a squared plus n pi over b squared. And that's your third representation of Green's function. What I'll do next is show how you can, how these different representations are related to each other. And for that, we'll need to use the calculus of residues. So anyway, let me just leave this up here for a minute.